Hi students, this is lecture number 8 and we are starting a new chapter on ionic and molecular compounds. For today's lecture we'll start on discussing what ions are and how they are involved in chemical bonds. Then we will go into detail about 3 categories of ionic bonding. First we will talk about simple ionic compounds made from main group elements, then move on to talking about ionic compounds from transition metals. Then lastly, we will talk about something called polyatomic ions. In nature, almost every element combines with something else to form compounds. And so compounds can be made by connecting atoms by 2 methods. One is called ionic bond, and 2 is called covalent bond. Ionic bonding will give you a compound sometimes called as salts, and covalent bonding will give you compounds known as a molecule. In this lecture, we will only focus on the first one, compounds made by ionic bonding. Let me take back that statement. Not all elements will form compounds. If you can remember, there was a class of element called the noble gases. They are in the group 8A, consisting of helium, neon, argon, krypton, xenon, and radon. It turns out that these elements exist in nature by themselves. They do not link up with any other atom. And the reason for this comes from their electron arrangement. Remember that the electron arrangement says in the first level you can have a maximum of 2 electrons, on the second level 8 electrons, on the third, fourth, and so on level have 8 electrons. So when we look at helium, it has 2 electrons, so it fills up completely the first shell. So this gives us our first noble gas. Moving on to the second shell, we have an element that has 10 electrons, 2 in the first shell and then 8 in the second shell. With 8 electrons in the second shell, it is again a complete shell, and this element is neon. And again, the pattern is that neon is a noble gas. From neon, we move on to the third shell with an element that has 18 electrons. 18 electrons mean it has 2 in the first shell, 8 in the second shell, and another 8 on the third shell. Again, filling up that shell completely. That element is argon, and again, argon is the noble gas. And it turns out there is something special about having a full shell of electrons. When you have a full shell of electrons, you are especially stable. And if atoms are like humans, we can say they are happy when they are stable. Because of this stabilization, atoms of the noble gas elements do not need to make bonds with any other atoms, even to another noble gas atom. That is why we can find a single atom of helium or argon in nature, just all by itself. You can't say this about other elements. Like oxygen is always found with others. For example, there are 2 oxygen atoms in the molecular oxygen that we breathe. And because of this stabilization, we have what is known as the octet rule, which states that all other elements want to achieve the same electron arrangement as the noble gases, with 8 valence electrons. A little side note to that is that there's also a duet rule, and this duet rule applies to hydrogen and helium, which are the first 2 elements because they only have 1 and 2 electrons respectively. So in simple terms, if you are an atom, your goal in life is to be like the noble gas. So how would you imitate the electronic arrangement of a noble gas? So speaking of electron arrangement, let's have a little bit of a review on that. The electron arrangement for chlorine is 287. The electron arrangement for sodium is 281. So for both of these atoms, you do not have a full octet. For chlorine, you have 7. You are 1 electron shy of a full octet actually. And then for sodium, you have 1 electron. You are very far away from a full octet. So what is an atom to do if it doesn't have an octet? Well, it turns out it can do of 2 things. It can either give or take electrons, or it can share it. In either of these methods, it creates something called a bond. So the first strategy will result in something that is called an ionic bond, where atoms can lose or gain electrons. A prime example of this is sodium chloride. The other strategy to achieving a full octet results in something called a covalent bond, and this strategy involves sharing electrons. A prime example of this, for example, is when chlorine and chlorine combine together and sharing electrons to make chlorine gas. We will discuss in detail covalent bonds in the next lecture. And so for this lecture, we will focus on ionic bonding only. So let's go back to this example of chlorine and sodium. Again, chlorine you see here has 7 electrons in its valence electron, so it just needs one more to make 8 electrons. Whereas sodium has 1 electron in its valence electron. So you can imagine sodium thinking, to have a full octet, I can either gain 7 electrons, take 7 electrons from someone else, or I can just simply give 1 electron away. And it turns out giving 1 electron away is so much simpler than taking 7 electrons from someone else. So you can imagine sodium and chlorine atom kind of striking a deal and saying, hey, if I give you my 1 electron, you can have 8 electrons as your valence electron. And at the same time, now since I have 0 electrons in my outermost shell automatically becomes the second level instead, which is already 8 electrons full. And so that's exactly what happens. The electron arrangement for both atoms are now full octets. Now since chlorine has received an electron, it now becomes more negative. And sodium, giving away electrons, becomes more positive. So we can't simply call them atoms anymore. Instead, we now call them ions. Chlorine ions and sodium ions. One is a positive ion and one is a negative ion. So let's focus on each of these ions one at a time. Let's first talk about the positive ions. The positive ions are the one who loses an electron. And remember, metals love to lose electron. And they will lose electron to obtain that octet. Once they lose that electron, their positive-negative balance is now off. Since now they have more protons than electrons, they will become a positive ion. A special name for a positive ion is called a cation. So let's go back to our example of sodium losing that 1 electron. Let's take a look at our periodic table for this example. Sodium is what element? The atomic number of sodium is 11. So that tells you that sodium has 11 protons and 11 electrons. So if you start out with 11 electrons and you lose 1 electron, how many electrons do you have left? You would have 11 protons and 10 electrons. Remember, each proton is positive 1 charge and each electron is negative 1 charge. So that you can see mathematically, if you have 11 positive and 10 negative, 11 plus negative 10 is positive 1. Because of this, sodium ion has a positive 1 charge. And to write the symbol for a cation, you write the positive charge as a superscript. If that positive charge is just 1, you do not actually write 1 plus, you just write the positive sign. If it is a 2 or 3 or 4 positive charge, then you would write 2 plus, 3 plus, 4 plus. Take a look at magnesium and predict how many electrons magnesium will lose to obtain that full electron shell. Again, to answer this, the simplest way is to take a look at what group magnesium belongs in. Magnesium is in group 2A. If you are in group 2A, you would have 2 valence electrons. And if you are a metal, you want to lose those 2 valence electrons. If magnesium loses 2 valence electrons, it will have the same electron configuration or electron arrangement as neon, so therefore it would be a happy noble gas-like ion. So magnesium is element number 12. That means it starts out with 12 protons and 12 electrons. If it loses 2 electrons, how many protons and how many electrons does it have? It will still have 12 protons, but only 10 electrons. So mathematically, that's 12 plus negative 10, giving you a positive 2 overall for its charge. So you can write magnesium ion as magnesium 2 plus like this. As a mnemonic device, a lot of students like to think of cations as being positive because the T in cation is like a positive sign. Another mnemonic device you may like is this definition of a cation. You can think of cation as an ion with a positive charge, and it's the cutest ion ever because it is a cat ion. Now let's take a look at the negative ions. Negative ions come from nonmetals. Because remember, nonmetals do not like to lose electrons, rather they like to gain electrons to obtain that octet. Once a nonmetal loses its electron, it becomes a negative ion, and that ion is called an anion. And going back to our chlorine example, we can see that chlorine is in group 7A, meaning it has 7 electrons. And in order to obtain noble gas electron arrangement, it must gain 1 electron to have that 8 electrons as its valence shell. To start off, Chlorine is element 17, so it has 17 protons and 17 electrons. If it gains one more electron, it is going to have a total of 18 electrons. So mathematically, 17 protons and 18 electrons mean you have 17 positive charges and 18 negative charges, giving you an overall charge of -1. And just like the positive charge, you can write the negative charge for anions. And in the same way, you do not need to write 1 minus if it's only -1 charge. Let's take a look at another example. Here we have oxygen. All right, I'm going to have you do this on your own. How many electrons would oxygen need to lose to be quote-unquote happy, like the noble gases? Oxygen is in group 6A. That means it has 6 valence electrons, meaning it will need to gain 2 more electrons. Oxygen starts with 8 protons and 8 electrons, and if it gains 2 more electrons, it will now have 10 electrons. Mathematically, that's 8 positives and 10 negatives. So 8 plus -10 is -2. So the symbol for the anion of oxygen is O2-. A mnemonic device to remember that anions are negative is that anions are like onions, and onions are bad, so they're negative, as opposed to cats are good, so that's positive. In the previous slides, I walked you through in detail why metals lose an electron and nonmetals gain an electron, metals becoming cations, nonmetals becoming anions, and we walked through how to write the charge of these ions. You don't have to do that every single time if you know the simple trend. The trick is to look at what groups the elements belong in. For example, if the element is in group 1A, they will always need to lose 1 electron, so they will always be 1 positive. For example, lithium will lose 1 electron to become similar to helium. Sodium will lose 1 electron to look like neon. Potassium will lose 1 electron to look like argon, so on and so forth. Whereas in group 2A, now you have 2 valence electrons that you need to lose, so you will have a positive 2 charge. Again, magnesium will lose 2 electrons to look like neon. Calcium will lose 2 electrons to look like argon, so on and so forth again. What about group 3A then? If you're in group 3A, you are going to lose 3 electrons. The same is true on the opposite side for nonmetals. If you're an element in group 7A, you have 7 valence electrons, so you always need 1 more electron. So you will gain 1 electron, and when you gain 1 electron, you automatically become a -1. So fluorine can gain 1 electron to look like neon, becoming fluoride ions F-. Chlorine will gain 1 electron to look like argon, to becoming a chloride ion, Cl-. Bromine will gain 1 electron to look like krypton, to becoming bromide ion, Br-. So you get the pattern. So if you're in 6A, you have 6 electrons, so you need to gain 2 electrons, so you will always be 2-. And if you're in 5A, you have 5 electrons, so you want to gain 3 electrons, so you will always be 3-. All right, let's go for a checkpoint. The question is, a fluoride ion has a mass number of 19 and an overall charge of -1. Identify the number of its subatomic particles. Pause to answer this. Alright, so to answer this, we need to know how many protons, neutrons, and electrons this ion has. We know that fluorine is an atom of element number 9, so it must have 9 protons. So we limit that down to A and B so far. What else do we know? If fluorine is going to be an ion, it must gain 1 electron, and it starts out with 9 electrons. Once it gains an electron, you have 10 electrons. Right, so the answer is B. But just double check to see if neutron counts is also correct. It has a mass number of 19, so 19 minus 9 is 10, so that's also good. So again, the answer is B. Alright, now that we have an understanding of what ions are, both cations and anions, let's see how they form bonds. Within ionic bonding, there are 3 categories that we will discuss. The first category of ionic bonding is what I like to call simple cations and anions. And what I mean when I say simple cations and anions is the one that come from the main group elements. But the main thing they share in common is that they involve ions. So to illustrate this point, let's take a look again at sodium and chlorine combining together in an ionic fashion. When sodium gives away its electron to chlorine, sodium becomes a positive ion, and when chlorine receives that electrons from sodium, chlorine becomes a negative ion. Now that we have a positive charge and a negative charge, what do we know about the attraction between a positive and a negative charge? Right? They are very strongly attracted to each other. This attraction is what we call an ionic bond. And this bonding occurs in a 1-to-1 ratio. For every 1 sodium, there is 1 chloride. The reason for this is charge balance. Most things in nature will be electrically neutral. So in order for the substance to be electrically neutral, the charge of the positive and the charge of the negative must be equal to each other to balance each other out, to cancel each other out. So mathematically we can see that the sodium is positive 1 and the chloride ion is negative 1. So positive 1 plus negative 1 is equal to 0. To annotate that when sodium and chlorine come together in a 1-to-1 fashion, we use subscripts. We can write sodium subscript 1, chloride subscript 1. But remember that whenever there's just a 1 in a subscript or a superscript, we kind of ignore it. So we can simply write this as NaCl without the subscript, and everyone would understand that this ratio is 1-to-1. The 1 is understood to be there. Now the subscripts become more important in a case like this. In this example, we will take a look at magnesium and chlorine. Again, magnesium has 2 valence electrons, so it needs to give away those valence electrons. One way it can give away those valence electrons is that it can give 1 to each of a chlorine atom, resulting in a magnesium 2+ ions and 2 chloride -1 ions. In this example, the ratio is 1-to-2. For every 1 magnesium ion, there are 2 chloride ions. And the reason for this, again, is to have a neutral charge balance. Mathematically, again, we can see that if you have 1 magnesium ion, that's a 2 positive. And if you have 2 chloride ion, each of those chloride ions is -1. So that's basically positive 2 plus -2 equals to 0. So to write this compound, we write Mg without a subscript because the subscript again is 1, and Cl with the subscript of 2. So if I give you a combination of any 2 elements, you should be able to write its formula. So how do we do this? So for example, if I say I have a compound and this compound is composed of chlorine atoms and calcium atoms, can you write me the ionic compound? The first thing you want to do is identify each as a metal or a nonmetal. In this case, the metal is calcium and the nonmetal is chlorine. Remember that ionic compounds can only occur between a metal and a nonmetal, because a metal will give its electron away, becoming a cation, and a nonmetal will gain those electrons and become an anion. A positive and negative are attracted to each other, and that attraction is called ionic bond. So for example, if I am tricky and I tell you what is the ionic compound that forms between calcium and sodium, what would you say? You should be able to recognize that calcium and sodium are both metals, so they would not form an ionic compound. Or if I tell you what is the ionic compound from chlorine and oxygen, you should also be able to recognize that chlorine and oxygen are both nonmetals, so they do not form ionic compounds. In fact, they do form bonds, but not ionic bonds, and we'll talk about that in the next lecture. And so the key, again, is to find the metal and the nonmetal. Next, you want to ask yourself how many number of valence electrons does each atom have? And remember, the valence electron count just comes from the group number. So calcium is in group number 2, so it has 2 valence electrons, whereas chlorine is in group number 7, so it has 7 valence electrons. Next, how many electrons must be lost or gained for each to have an octet? So calcium has 2 valence electrons, so it should lose 2 electrons, whereas chlorine has 7 electrons, is a nonmetal, so it's going to gain 1 electron. So from this last information, can you write the symbol for the ions? So if a calcium loses 2 electrons, it's going to be calcium 2+. If chlorine gains 1 electron, it's going to be chlorine minus. And the last step is to consider the ratio of the 2 ions that will result in a net charge of 0. So from our last step, we have decided that we have a calcium 2+ and a chloride -1. So that calcium has a 2 plus charge, so you would need 2 chloride ions because each of those chloride ions is only 1. So if you have 2, you have a net charge of negative 2. And negative 2 plus positive 2 will give you 0. From that, you can write the ionic compound formula as CaCl2. Now there is another trick to writing this a little bit more quickly, and that trick is to take the charge of the cation and make the positive number as a subscript of the anion, and then vice versa. So what do I mean by this? So again, we know that calcium is 2 plus and chloride is minus 1. So you take that charge of 2 and put it as simply as a subscript of chloride, and if you take that minus 1 and put it as a subscript for calcium, you should get Ca1 and Cl2. Again, getting rid of that 1, we come to our same conclusion that the formula is CaCl2. So this trick will work most of the time. Where it doesn't work is when you have a ratio that is not its most reduced form. In our last example of CaCl2, it's a ratio of 1 to 2, and that is the most reduced ratio possible. As opposed to this next example, if you have an ionic compound composed of calcium 2 plus and oxygen 2 minus, you might be tempted to put that 2 plus down to the oxygen side and that 2 minus down to the calcium side, giving you Ca2O2. So here the ratio is 2 to 2, but notice that this is not its most reduced form because 2 to 2 is the same as 1 to 1. So you can write it as CaO, and this is called its formula unit. And the reason why we use the formula unit is that you can imagine that you can write a ratio of 1 to 1 in many ways. You can write it as Ca3O3, Ca4O4. You see that it's a 1 to 1 ratio. And it turns out the actual compound is a lot more than 1 atom to 1 atom. It could be a billion calcium atom to a billion oxygen atom, right? So to simplify things, we want to be able to write it in its simplest ratio. So let's have a checkpoint. Can you write the correct formula for the ionic compounds that result from magnesium and nitrogen? Alright, pause and work on this. Alright, so hopefully you recognize that magnesium will be a positive 2 cation and nitrogen will be a negative 3 anion. So in order for them to be charge neutral, they will have a ratio of 3 to 2. So you would write it as Mg3 and 2. And you can always check your formula by doing the charge balance. In this case, we said the ratio between magnesium and nitrogen is 3 to 2. That means that we have 3 magnesium 2 pluses for every 2 nitrogen 3 minuses. Mathematically, that means it's 3 times a positive 2 plus 2 times the negative 3. And if that equals 0, then we are charge balanced. Right? 3 times 2 is 6, and 2 times negative 3 is negative 6. So positive 6, negative 6 does equal to 0. That means that we have the right ratio. And 3 to 2 is the most reduced form, so that must be correct also. Now let's talk about naming the elements. And we will take the compound form from calcium and chlorine as our example. The first step in naming the ionic compound is to first name its cation, which is the metal. In this case, which one is our metal? It's the calcium. The next step is to take the base name of the anion. In this case, what's our anion? Chlorine, right? For chlorine, the base name is chlor. You just basically get rid of the last ending, the last syllable. Lastly, you replace that last syllable with an IDE, ide, so chlorine becomes chloride. So the name for this compound is calcium chloride. Let's do another example. What about calcium and oxygen together? Your metal there is calcium, your nonmetal is oxygen. The base name of oxygen is ox, so the name of this compound is calcium oxide. What about lithium and nitrogen? Lithium is your metal. Metals will always go first, both in the formula and in the name. So that's going to be lithium nitride. And again, this kind of naming will only work if you have main group metals. So let's take a look when it is not a main group element. So for example, naively, we can say that this element is called cobalt chloride because the metal there is cobalt. The anion there is chloride. Well, it turns out in nature, this compound also exists. Instead of 2 chlorides, there is 3 chlorides. Would you also call this cobalt chloride then? Now to contrast this, we can take a look at a compound like this, MgCl2 versus MgCl3. Now we know for sure that MgCl3 does not exist because the charge of magnesium we know is always going to be positive 2. So because that charge is positive 2, it always only need 2 more chlorides because each chloride is negative 1. So when we say magnesium chloride, we always will mean MgCl2. On the other side, when we say cobalt chloride, we could mean CoCl2 or CoCl3. Reason for that is because cobalt is a transition metal. It turns out transition metals, when they lose electrons to become a cation, they can lose it in many ways. If they lose only 1 electron, they will be a positive 1. If they lose 2 electrons, they will have a positive 2. If they lose 3, 4, 5 electrons, they will be positive 3, positive 4, positive 5, respectively. So if you have a transition metal as your cation, it becomes a little bit more complicated and you have to apply a different set of rules. We can't use the rules that we just talked about. This brings us to our next category of ionic compounds, what we call a variant charged cation. The word variant here means that it varies, right? So sometimes it could be positive 1, positive 2, etc. Whereas when you are a main group element in the first category that we talked about, that's called an invariant. It doesn't change. If you are in group 1A, you always will be positive 1. If you are in group 2A, you're always going to be positive 2 as cations. But when you are a transition metal, all bets are off. So to combat this, we have to use something called Roman numerals to tell us what is the actual charge of that cation. And to know the charge of the cation, you would have to be given the charge, or the charge is implied in an ionic compound, in which case you have to derive the charge. So for example here, when you have CoCl2, what is the charge of that CO? If ionic compound has 2 chlorides and only 1 cobalt, that must mean that the cobalt is a 2 positive charge. How do I know that? Well, because each chloride we know is invariant. It will always be negative 1. So if it is negative 1 and there's 2 of it, the negative charge in there is negative 2. So to balance it out, the cobalt must be a positive 2. Positive 2 plus negative 2 is 0. So that is a very important step. You must know what is the charge of your cation. You must know that the anion charge will always be the same, and from the charge of the anion and how many anions you have, you can figure out what is the charge of your cation. So in this case, we have decided that it's going to be cobalt 2+. So to name it, you simply again give the name of the metal. In this case, it's cobalt. Next, you want to put the charge of that cation in a parentheses in Roman numerals. In this case, it is Roman numeral 2, and then the rest of the name is nothing new. You put the base name, which is chlor, and then end it with I. So this is cobalt 2 chloride. Let's do another example. How about CoCl3? How would you write the name of this compound? Again, first realize that cobalt is a transition metal, so it is going to have variant charges. So in order to know its charge, we look at its anion. In this case, we have 3 chlorides giving us a negative 3 charge. So cobalt must be positive 3. If cobalt is positive 3, this is going to be called cobalt 3 chloride. Okay, so let's recap what we have talked about so far. We talked about that main group elements, when they become ions, they will be invariant ions. So again, let's take a look at the metal side. If you're in group 1A or in group 2A, you are a main group element of metals, so you will always have the same charge. Group 1A will always have positive 1. Group 2A will always be positive 2. And if you are in group 7A, you are always negative 1. Group 6A, you are negative 2. Group 5A, you are negative 3. You will never change. That's why it's called invariant. As opposed to when you are a transition element, when you become a cation, you will have various charges. Some example given here: chromium, you can be 2+ or 3+. Manganese, you can be 2 or 3+. Iron, you can be 2 or 3+, so on and so forth. Well, it turns out there are also exceptions that you should memorize. There are 3 transition metals that are different. They will always have the same charge, just like the main group element. And those 3 elements are zinc, cadmium, and silver. Zinc will always be a 2+, cadmium will always be a 2+, and silver will always be a 1+. Because they are invariant, when you name them, you do not need Roman numerals. Alright, let's try to see if you can do this backwards. If I give you the chemical compound name, can you write the chemical formula? So in our first example here, let's go with nickel 2 chloride. You first need to identify the charges in your ion. Nickel 2 tells you that the nickel has a positive 2 charge, and chloride, you know, will always be negative 1. Knowing that you have nickel 2 plus and chloride minus, what's the ratio that will give you charge balance? So that's something we've done before in the first category, right? So that becomes NiCl2. You need 2 chlorides to balance out with the 2 plus nickel. What about the second case? Nickel 3 chloride. Then you need to find out what the charge of the cation is. In this case, nickel 3 means it's nickel 3 plus, so therefore that is NiCl3. I want to emphasize what the 2 and 3 mean in the name. The 2 and the 3 means that's the charge of the metal. A common mistake that students often make is they think that that 2 is a subscript. So for nickel 2 chloride, they write nickel subscript 2 Cl. And for nickel 3 chloride, they write nickel subscript 3 Cl. So don't make that mistake. Now let's talk about trickier cases. For example, if I have a compound composed of iron and oxygen, we first recognize that iron is a transition metal. So we can't simply say iron oxide. We have to say what is the charge of that iron. To find out the charge of the cation, always take a look at the anion. In this case, it is oxygen 2 minus. Since there's only one oxygen 2 minus, the charge of the negative is 2 minus. So you ask yourself, what must the charge of the iron be to cancel out this? And the answer for this is that iron must be a positive 2 charge, giving us the name iron 2 oxide. The 2 again says that the iron is a positive 2 charge. Another example, Fe2O3. The oxygen still has a negative 2 charge, always. In this case though, there are 3 oxygens, so 3 times 2 minus is negative 6. To cancel out that negative 6, you must have positive 6 contributing from your iron. In this case, the subscript on the iron is 2. So if you have 2 ions of atom, it must add up to positive 6. So what must each of those iron ion charge be? The answer is it must be positive 3, because 2 times positive 3 will give you positive 6. Again, the iron will give you positive 6. The oxygen will give you negative 6. Positive 6 plus negative 6 is 0. So that tells you that is the correct charge of iron in this case, giving us the name iron 3 oxide. The 3 again signifies the charge of the iron. I would say that many students will struggle with this, and with enough practice and the questions you may ask in class, hopefully this will become clear to you. Moving on to our last category of ionic compound is when the ionic compound involves something that is called polyatomic ions. Everything that we talked about before this point, the ions in those examples are called monoatomic. Mono meaning one. And now in this section we will talk about polyatomic, poly meaning many. For example, your cast is made up of a substance that is CaSO4. Ca is your ion and SO4 is also your ion in this compound. Your positive charge, your cation, is calcium and is only one type of element, calcium. That's called a monatomic ion. Whereas sulfate is composed of multiple atoms. Because it is composed of multiple nonmetals that has one single charge, we call that a polyatomic ion. Another example is your fertilizer. It is made of a polyatomic ion called ammonium as your cation and nitrate as your anion. Both of these are polyatomic ions. There are many polyatomic ions, and here's a list of them. Highlighted in red asterisks are the ones that I asked that you memorize for this class. You need to memorize its name, its formula, and its charge. For example, the first one, hydroxide. You need to know that it is composed of 2 elements, oxygen and hydrogen, and together they are a negative 1 charge, meaning they are anions. It turns out all of them are anions except for one. Ammonium is the only polyatomic cation. Its formula is NH4 and it has a charge of positive 1. You also need to know nitrate, which is NO3, negative 1. You need to know chlorate, ClO3, charge -1. You need to know carbonate, CO3, charge 2-. Hydrocarbonate or bicarbonate means the same thing, is HCO3 with charge -1. Cyanide is CN, charge -1. Acetate is C2H3O2, that's a long one, has a charge of -1. Sulfate, SO4, 2-. And phosphate, PO4, 3-. I recommend you making flashcards to memorize these polyatomic ions. Now the good thing about naming ionic compounds containing polyatomic ions is that they're quite simple. So for example, if you have sodium and chloride here, its name is simply adding the name of the metal plus the name of the polyatomic ion. So that's sodium chlorate. And of course, if it's a transition metal as a cation, you also need to follow the rules of including Roman numerals. But in this case, it is not. Notice that you don't change the ending if your anion is a polyatomic anion. You keep it as chlorate and not chloride. And if you have ammonium, you simply say ammonium. So you just say, in this case, ammonium chloride. Again, it's chloride because your anion is the chlorine. All right, so let's have a final checkpoint. What is the formula of iron 3 hydroxide? Pause and do this problem. All right, hopefully you made some progress. First, from the name, we know that it is Fe3+, and you also recognize that hydroxide is a polyatomic ion, OH -1. So if each OH is -1, you would need 3 of the OHs. You need 3 of the hydroxides to cancel out your 1 iron. So mathematically, it looks like this to give you that charge balance, giving you the ratio of 1 to 3. So to write the formula for polyatomic ions, you need that whole parentheses. The parentheses there says you have 3 of the OH. Without writing the parentheses, that 3 would only apply to the hydrogen, and you would have 3 hydrogens, 1 oxygen, and 1 iron, which is not the case. We're trying to say here that for every 1 iron cation, you have 3 hydroxides, meaning 3 oxygens and 3 hydrogens. So that parentheses is very important. So the answer here is C. Okay, so let's have a summary of how to name ionic compounds. Hopefully this flowchart will help you get the hang of things. First, in an ionic compound, you must realize that there's going to be your cation and your anion. Your cation will be a metal or NH4, and your nonmetal. Let's focus first on the cation. You first ask yourself, does the metal form 1 positive ion or does it form more? If your answer is 1, and that's because it's a metal that is in group 1A, group 2A, group 3A, or if it's zinc, silver, or cadmium, then you just use the name of the element. Or if it's ammonium, you just use the name of ammonium. Or if you answer that it can form more than 1 positive ion, because it is a transition metal, or in group 4A or in 5A, then you want to use Roman numerals to designate the charge of that cation. On the anion side, you want to ask, is the nonmetal ion formed from 1 atom or groups of atoms? If you answer that it comes from 1 atom, then it's called a monatomic ion. And you want to change the ending to "ide." If it's a group of atoms, then it's a polyatomic ion. You don't change the ending, you just use the polyatomic ion's name. Alright, so that's the end of lecture 8. By the end of this lecture, hopefully you are able to write the symbols for simple ions. You are able to use the charge balance to write the correct formula for a compound. And if you are given the formula of a compound, you can write the correct name, vice versa. Both in the case where you have main group elements or in the case where you have transition elements. And lastly, you should be able to write names of polyatomic ions and their formulas.